Welcome to the science.com classes. Today I am going to discuss about Hamiltonian dynamics. In this lecture, I teach you how to construct a Hamiltonian from a Lagrangian. So, in many of the set question, gate question or net questions, they given one Lagrangian and they asked to find out the corresponding Hamiltonian. This one is a almost sure question. In every exam you can see this question. So this one is a very important topic. Okay. And how we can construct a Hamiltonian from a Lagrangian? This is a question. So we need a mathematical tool to do this transformation, and that mathematical tool is called Legendre transformation. Through Legendre transformation, the Lagrangian and Hamiltonian are connected. See, this one is a previous set question. The Lagrangian and Hamiltonian of a system are related through Legendre transformation. So by using this mathematical tool, the Legendre transformation, what we are doing? We are converting a Lagrangian, and you know Lagrangian is a function of q dot and t, and we are transforming it into a Hamiltonian, and Hamiltonian is a function of q, p and t. Here you know q dot is velocity, that is generalized velocity, and this p is generalized momentum. See, in Lagrangian, q is there, t is there. In Hamiltonian also, q is there and t is there. But the velocity q dot is replaced by momentum p. That is the main difference between Lagrangian and the Hamiltonian. And there is a question, why Hamiltonian? Because we already have Lagrangian and we practiced many questions. Then why Hamiltonian? The answer is, you know, the Lagrange's equation of motion, that is d by dt dou L by dou q dot minus dou L by dou q equal to 0. And by solving this equation, you get 2n plus 1 second order differential equations. And the Hamilton's equation of motions are q dot equal to dou h by dou p and p dot equal to minus dou h by dou q and dou h by dou t equal to dou L by dou t. Here, by solving these equations, you get 2n plus 1 first order differential equations. See, here it is second order differential equation and here it is first order differential equation. Then also you have a doubt. Even if it is second order differential equation or first order differential equation, then what is the problem? Okay, I tell you. That is, by solving this equation of motion, what we get? We get q double dot. We get acceleration in generalized coordinates. Okay, that is, it is equal to d square q by d t square. We know this q is the coordinate. Coordinate is q. So to find out q from the equation of motion, what you have to do? You have to do double integration over this q double dot. Then only we can find out the coordinate of the system. And here in this equation you see, what is the equation of motion? That is q dot is equal to dou h by dou p. Here to find out coordinate, that is q, you have to do one integration. So integrating one time is easier than integrating a function two times, because sometimes we get very complex equations, then integrating we get another complex equation, then again integrating that function is very complex. So here you see, when we are using a Hamilton's equation of motion, we can find out the coordinate just by one integration. That is the advantage of constructing the Hamiltonian. Now, the relation between Lagrangian and the Hamiltonian. We know Lagrangian is a function of q, q dot and the t. Now, I am taking dl by dt. Then what we will get? We get dou L by dou Q into dou Q by dou T plus dou L by dou Q dot by dou T plus dou L by dou T. Right? I can rewrite this equation because we know dou Q by dou T is Q dot and dou Q dot by dou T is Q double dot. So I can rewrite this as dl by dt equal to dou L by dou Q into Q dot plus dou L by dou Q dot Q double dot plus dou L by dou T. Again, I can rearrange this equation as dl by dt equal to d by dt of Q dot dou L by dou Q dot plus dou L by dou T. You do one thing, maybe you have some confusion. You please do this differential d by dt Q dot dou L by dou Q dot. I tell you, by doing those differential, you get this function. Okay. Anyway, you just try by yourself. Here I am rearranging this function once again. That is, I am bringing this term to left hand side. So I get d by dt L minus Q dot dou L by dou Q dot equal to dou L by dou T. And you see, if this Lagrangian is independent of time, that is, Lagrangian is not explicitly dependent on time, then we get 0. Or we can say, if t is cyclic coordinate, that is, cyclic coordinate is the missing coordinate in the Lagrangian, then this entire function L minus Q dot dou L by dou Q dot is a constant. And we call this entire term as Jacobi's integral. Here once again I am rearranging this equation, that is d by dt of Q dot dou L by dou Q dot minus L equal to minus dou L by dou T. I multiplied throughout by minus, right? And here, you know this term dou L by dou Q dot, it is nothing but P. P is equal to dou L by dou Q dot. So I can rewrite this equation as d by dt Q dot P minus L equal to minus dou L by dou T. And here I am calling this function as Hamiltonian function. That is represented by h. So I can write the Hamiltonian h equal to Q dot P minus L. And here you see the Q is generalized coordinate and it may be 1, 2, 3 or up to n coordinates. So we need a summation sign, that is summation I, Qi, Pi minus L. This is very important equation. Okay. We are going to use this equation to construct Hamiltonian from Lagrangian. So this is a very important equation. And here I tell you one more thing. If this Lagrangian L is independent of time, that is, it is not a function of time, then you get d by dt of Q dot P minus L equal to 0. Then you can definitely say this function, that is Hamiltonian function, is a constant because derivative of a constant is 0. Okay. So if Lagrangian is not a function of time, then Hamiltonian will be a constant. Remember this one also. So what is the equation to construct or transform Lagrangian to Hamiltonian? It is H equal to summation I Q dot P minus L. And here, what is this P? P is equal to dou L by dou Q dot. Suppose in a question they are given Hamiltonian and they are asked to find out Lagrangian. Then which equation we will use? Yeah, we just rearrange this equation that we get L equal to summation Q dot P minus H. This equation to transform Hamiltonian to Lagrangian. If in a question Hamiltonian is given and they are asked to find out the Lagrangian, then you use this equation. And if Lagrangian is given and asked to find out the Hamiltonian, you use this equation. Okay. And I tell you one more thing. Here you know Hamiltonian is a function of Q, P and T, and Lagrangian is a function of Q dot T. So in this question, in a question to construct Hamiltonian from Lagrangian, in the final equation, that is final equation is the equation of Hamiltonian. In that equation, there will not be any Q dot term. So if there are any Q dot term, you convert it into P term. Okay. So what you have to do? You have to replace this P term. To replace this P term, you have to use this equation that is dou L by dou Q dot. So you get a relation between P and Q dot. Then you use that equation, that relation to replace this P. So what you get? You get Hamiltonian in terms of Q, P and T. That is, you have to replace every Q dot term in the right hand side of this equation to corresponding P term. Then only we get Hamiltonian in terms of Q, P, T. Okay. Example problem. A Lagrangian is given in Cartesian coordinate system. You know Lagrangian in Cartesian coordinate system, it is equal to 1 by 2m x dot square plus y dot square plus z dot square minus v. And the question is to find corresponding Hamiltonian. Then what we will do? We know the equation relating Hamiltonian and the Lagrangian, that is summation I Q dot P minus L. And I told you Hamiltonian is a function of QPT. So what you have to do? We have to replace this Q dot terms in the Lagrangian. So what are these Q dot terms here? That is generalized velocities here. One is x dot, y dot and z dot. So we have to replace these equations in terms of P. Then only we get Hamiltonian in terms of QPT. So what is the procedure? So the procedure is, in the given Lagrangian, you have to first identify the generalized coordinates. So here the generalized coordinates are x, y and z. Then find out the corresponding generalized momentum. What are the generalized momentum? Px, Py and Pz. And what is this Px? Px equal to dou L by dou x dot. So what we get? We get it is equal to m x dot. And what is Py? Py is equal to dou L by dou y dot and it is equal to m y dot. And what is Pz? Pz is equal to dou L by dou z dot and that is equal to m z dot. So see, we can replace x dot term in terms of P. How? We get x dot equal to Px by m and here y dot is equal to Py by m and z dot is equal to Pz by m. So the relation between Hamiltonian and Lagrangian is summation q dot I p minus Lagrangian. Now I am going to expand this function, that is h is equal to summation I qi dot pi. So here you know there are three generalized coordinates, that is q1 is x, q2 is y, and q3 equal to z. So this summation is from I equal to 1 to 3. So what we get? We get q1 dot is x dot p1. So p1 will be here, it is equal to px, p2 will be equal to py, and p3 will be equal to pz. So x dot px plus y dot py plus z dot pz minus Lagrangian. Lagrangian is 1 by 2 m x dot square plus y dot square plus z dot square minus v, that is plus v. Here I told you Hamiltonian is a function of q, p, t. So what we have to do? We have to replace every dotted terms. We have to replace x dot, y dot, z dot. Okay, we have to replace all these functions. So how we replace? We can replace this x dot by px by m, and we can replace this y dot by py by m. So what we get? We get h equal to x dot is px by m, px plus py by m, py plus pz by m, pz minus 1 by 2 m into x dot square is px square by m square plus py square by m square plus pz square by m square plus v. Now we can subtract this term from this one. So what we get? We get h is equal to px square by 2m plus py square by 2m plus pz square by 2m plus v. This is the Hamiltonian, corresponds to Lagrangian in Cartesian coordinates. Another example. Construct Hamiltonian. The given Lagrangian is plane polar coordinates. Lagrangian in plane polar coordinates. What is Lagrangian in plane polar coordinates? It is equal to 1 by 2 m r dot square plus r square theta dot square minus v. So what is the procedure? First you have to find out generalized coordinates. What are the generalized coordinates? R is there and the theta is there. And then we have to find out generalized momentum. What is it? PR and the p theta. What is PR? PR equal to dou L by dou R dot. What we get? We get m r dot. And what is p theta? P theta is dou L by dou theta dot is equal to m r square theta dot. So we can find out this r dot value, that is equal to PR by m, and theta dot is equal to p theta by m r square. Now what is the equation relating Hamiltonian and Lagrangian? Hamiltonian equal to summation I qi dot pi minus Lagrangian. So here the generalized coordinates are q1 is r, q2 is theta, and p1 equal to pr and p2 equal to p theta. So we have to do this summation, that is we get h is equal to q1, that is r pr plus theta p theta minus Lagrangian. Lagrangian is 1 by 2 m r dot square plus r square theta dot square minus v, that is plus v. Sorry, I forgot to put this r dot theta dot. Okay, now what we have to do? We have to replace all these dotted terms, because Hamiltonian is a function of Q, P and T. So in Hamiltonian there will not be any Q dot terms. Okay, so we have to replace every Q dot terms in this equation. Then only we get the Hamiltonian. Okay, so what is R dot? We know R dot is equal to PR by M. That is H is equal to PR by M into PR plus what is theta dot? That is P theta by MR square P theta minus 1 by 2 M. R dot square is PR square by M plus R square P theta square by M square R raised to 4. Here I forgot to put this square. Okay. Plus V. Now we can subtract this term from this one. See, this M and square will cancels. And this R square and this R raised to 4 will cancels. So what do you get? We get Hamiltonian H is equal to P R square by M plus P theta square by M R square minus 1 by 2 P R square by M minus 1 by 2 P theta square by M R square plus V. So finally we get Hamiltonian as 1 by 2 P R square by M plus 1 by 2 P theta square by M R square plus V. This is the corresponding Hamiltonian in plane polar coordinates. A small work for you. Find out Hamiltonian for Lagrangian in cylindrical coordinates. I help you a little bit. We know Lagrangian in cylindrical coordinate is 1 by 2 M rho dot square plus rho square phi dot square plus Z dot square minus V. So what are the generalized coordinates? First step is we have to find out generalized coordinate, and the generalized coordinates are rho, phi, this is rho, phi and Z, the dotted coordinates, the coordinate which have bindi, right? Okay, then what do you have to find out? We have to find out the generalized momentum, that is P rho, P phi and Pz. We know P rho is equal to dou L by dou rho dot and P phi is equal to dou L by dou phi dot and Pz is equal to dou L by dou Z dot. So from here you get the relation between rho dot and P rho. Here you get relation between phi dot and P phi, and here you get relation between Z dot and Pz. And here Q1 equal to rho, Q2 equal to phi and Q3 equal to Z, and P1 equal to P rho, P2 equal to P phi and P3 equal to Pz. Now what we have to do? We have to write the equation for Hamiltonian, that is summation Qi dot P minus L. So what we will get? We get H equal to rho dot P rho plus phi dot P phi plus Z dot Pz minus Lagrangian, that is 1 by 2 M rho dot square plus rho square phi dot square plus Z dot square minus V, that is plus V. Now we have to replace all these dotted coordinates. In Hamiltonian we are not interested in those peoples with the bindi. Okay, so we don't want these dotted terms. So we have to replace this all dotted term by our P, and that P value you will get from these relations. Okay, so please replace all these dotted terms and find out the Hamiltonian. One more work for you. Find Hamiltonian in spherical polar coordinate system. I think you know the Lagrangian in spherical polar coordinate system. It is equal to 1 by 2 m r dot square plus r square theta dot square plus r square sine square theta phi dot square minus v. Now first you have to find out the generalized coordinate. Then you have to find out generalized momentum. Then write the equation for Hamiltonian. Then replace all q dots, that is r dot, theta dot, phi dot terms in the equation. So you get the Hamiltonian. Okay. I know you all are familiar with Bill Gates, the Microsoft CEO, and there is a quote by Bill Gates. The quote is like this: I always choose a lazy person to do a hard job because a lazy person will find an easy way to do it. So, if you are a hard-working guy, then you will find out the generalized coordinate, then you find out the generalized momentum, then you find out Hamiltonian, then you replace all the r dot, theta dot and phi dot terms. Then finally you will get the Hamiltonian. But lazy people will never do this work. They will go for easy jobs, that is tricks. So I tell you some tricks to solve these problems in very easy way. I follow these tricks because I am very lazy. Okay, so what is the trick? The trick. Here I am considering the Lagrangian in Cartesian coordinate system. So you know Lagrangian in Cartesian coordinate system, that is 1 by 2 m x dot square plus y dot square plus z dot square minus v. And just now we find out the corresponding Hamiltonian, that is h equal to p x square by 2m plus p y square by 2m plus p z square by 2m plus v. Here I am rewriting this Hamiltonian, that is h is equal to 1 by 2 into 1 by m into px square plus py square plus pz square plus v. Now I am going to compare this Lagrangian and this Hamiltonian. See, what is the first term? First term in Lagrangian, it is 1 by 2. Here in the Hamiltonian also 1 by 2 is there. It is same as in the Lagrangian. Now check the second term, that is m. Here you see in Hamiltonian m is inverted, and here x dot square, y dot square, z dot square, and these are replaced by px, py, pz, that is generalized coordinates replaced by generalized momentum. And this sign, minus sign, here in Hamiltonian it become plus sign. So sign is opposite. So to construct a Hamiltonian from a Lagrangian, what you have to do? If there is a 1 by 2 term, constant term, you have to write the term same as in the Lagrangian. And the remaining coefficient of x dot square, y dot square, z dot square will be 1 by that term. That is, here it is m, so it become 1 by m. And the generalized coordinate are replaced by corresponding generalized momentum, and negative sign before potential will be changed to positive sign. If it is a positive sign, it become negative sign in the Hamiltonian. So remember these things. Then you can easily write any Hamiltonian from Lagrangian. But there is some restrictions. This trick is not valid for all problems. I tell you what kind of problems we can solve by this trick and what kind of problems we can't solve by this trick. Okay, don't worry. Now the example problem. Lagrangian is given. Lagrangian in spherical polar coordinate system, that is 1 by 2 m r dot square plus r square theta dot square plus r square sine square theta y dot square minus v. Now construct the Hamiltonian. What will be the Hamiltonian? See, 1 by 2 term is there. It will be same. We have to write it as here, 1 by 2. Then what is the remaining term? That is the coefficient of r dot square theta dot square is m. So that become 1 by m. The generalized coordinate replaced by generalized momentum. That is for r coordinate momentum is pr. That is pr square plus. Here I told you, see, this is a coefficient of theta dot term. So we have to take inversion of this one. That is 1 by r square. Theta is p theta square plus here this also coefficient of phi dot term. So 1 by r square sine square theta p phi square. And this minus sign is become plus v. So this is the corresponding Hamiltonian. Another example problem. Lagrangian is equal to 1 by 2 m rho dot square plus rho square phi dot square plus z dot square minus v. That is Lagrangian in cylindrical coordinates, right? What is the corresponding Hamiltonian? See, first term 1 by 2. Now change. You have to write it here also. Into m. What do you have to do? You have to invert 1 by m. Into rho dot square. So we have to find the corresponding momentum, that is p rho square plus, see, this one is a coefficient of phi dot. So we have to take its 1 by rho square and p phi square plus p z square plus v. That is sign becomes opposite. So we got the Hamiltonian in cylindrical coordinates. Then please find out the Hamiltonian for following problems. Third one, that is Lagrangian equal to 1 by 2 m L square theta dot square plus mg L cos theta. Here this one is the potential. Fourth one, L equal to 1 by 2 I theta dot square plus mg L cos theta. Here also mg L cos theta is the v. Fifth problem, L is equal to 1 by 2 m r square sine square theta phi dot square plus mg r cos theta. Sixth problem, L equal to 1 by 2 m x dot square plus L plus x all square theta dot square plus mg L plus x cos theta. Seventh problem, L equal to 1 by 2 x dot minus v of x. And eighth problem, L is equal to a x dot square plus b y dot square minus k xy. And ninth problem, L equal to 1 by 2 m x dot square minus 1 by 2 k x square plus k x cube plus beta x dot square. Here you please use this trick. Just look into the Lagrangian and just write the corresponding Hamiltonian. Okay, it's a simple job, right? Now let us discuss some previous question papers. This one is a previous set question. And the question is to find out or construct Hamiltonian from Lagrangian. So here, first you have to check the sign of the potential term. Here it is minus mgl cos theta. And I told you when it is converted to or transformed to Hamiltonian, the sign will change. In Hamiltonian, the sign of potential term will be opposite. So for this case, it will be plus. So this may be the option or this may be the option. And these two are not the correct options. Now use the trick. So by using the trick, you can find out this one. Option A is the correct answer. This one is a gate question. And it is same as the earlier question. So here also you check the potential term. So maybe this will be the answer or this will be the answer, right? And when doing this trick for this kinetic energy term, you can find out option B is the correct answer. So if you know this trick, then these problems are very easy, right? Here this one is a previous net question, CSIR net question. See the Lagrangian, given Lagrangian is 1 by 2 m q dot square minus lambda by 2 q dot square. The question is to find out the Hamiltonian, right? Here you see, here q dot square is there, here also q dot square is there. So I can rewrite this equation as L is equal to here 1 by 2 also a common term. I am taking this out. That is 1 by 2 into m minus lambda q dot square. Now you just apply our trick. So 1 by 2 will be same into the coefficient of q dot square will be inverted, that is m minus lambda q, and q will be corresponding momentum, that is p square. So which one is the answer? Option B. This is another CSIR net problem. Here the Lagrangian is equal to x dot square by 2x minus v of x. So Hamiltonian will be equal to this 2 term we have to take outside, that is 1 by 2 into coefficient of x dot square is x and we have to take its 1 by. So we get x into, we have to replace this generalized coordinate into generalized momentum, that is px square, minus become plus v of x. So I think you got the answer, that is option A. This one is a previous gate question, and here our trick will not work. We have to solve this problem in the proper way. We have to solve this problem in the proper way. That is, we know the relation between Hamiltonian and Lagrangian, that is h is equal to q dot p minus L. So the given Lagrangian is L equal to m by 2 v square plus cr v minus v of r. Here these two are velocity term and we know velocity v vector is equal to r dot vector. So I can rewrite this equation, that is L equal to m by 2 r dot square plus c r dot minus v of r. Now what is our method? First you have to find out the generalized coordinate. Here the generalized coordinate is r. And the next step is to find out the corresponding generalized momentum. So that is PR. And PR will be equal to dou L by dou R dot. So what we will get from this Lagrangian? We get MR dot plus CR. So we can find out this R dot value. That is R dot will be equal to PR minus CR by M. Now third step is write the Hamiltonian, that is summation Q dot P minus L. So the Hamiltonian H will be equal to Q dot is here R dot, P minus L is M by 2 R dot square minus CR R dot plus V of Now we have to replace all these terms, r dot terms, because in Hamiltonian there will not be any velocity terms. Okay, so it is equal to r dot is we know PR minus CR by M into PR minus M by 2 r dot square is PR minus CR by M all square minus CR into PR minus CR by M plus V of R. Here you can see this term and these terms are common and we can take PR and CR. So I can rewrite this equation as follows. That is H is equal to PR minus CR by M into PR minus CR minus M by 2 PR minus CR by M all square plus V of R. So here what we get, this is equal to PR minus CR all square by M minus, here you can cancel this 1m and 1m square. So we get 1 by 2 PR minus CR all square by M plus V of R. So what we get, H is equal to PR minus CR all square by 2m plus V of R. So what is the answer? Option B, right? Don't worry, it is PC because in the question itself it is specified PC is the canonical momentum. Okay, so option B is the correct answer. Here I told you a trick to construct Hamiltonian from Lagrangian. You just look into the Lagrangian and just write the Hamiltonian. So the trick is very powerful, but I told you the trick has certain limitations. Even in the last problem, we never used the trick. We followed the original procedure. Why? Because the trick is not applicable to that problem. So what are the limitations of the trick? Where we can apply the trick and where we can't apply the trick. So first I tell you where we can apply this trick. We can apply this trick if potential V is a function of R only. That is, R is position coordinate. So if potential is a function of position coordinates only, then we can use this trick. And where it is not applicable, the first condition, if potential is a function of velocity, that is velocity dependent potential, then we can use this trick. And if potential is a function of time, if it has a explicit time dependence, then also we can use this trick. And third one, if the kinetic energy having cross terms, that means maybe it's a product of two velocities Vx, Vy, that is x dot, y dot kind of things. So if there is cross terms in the kinetic energy, then also the trick is not valid. So before using the trick, you should be very careful. Okay. Now I am going to teach you another trick. Trick to construct Hamiltonian if L is given. This trick is applicable to all, but this trick is little more difficult than earlier trick. But the advantage is it can be used to any problem. Okay, so the trick is, before telling the trick, I will tell you one example. Let us consider a Lagrangian L equal to 1 by 2 m x dot square plus y dot square. Here I am going to rewrite this equation in terms of matrix equations. So I am rewriting this as 1 by 2. I am writing a matrix that is x dot y dot into some square matrix into x dot y dot. So here you see, if I substitute m here and 0 here, 0 here and m here, then you do the matrix multiplication, you get the same equation. Okay, so this is a matrix form of Lagrangian L equal to half m x dot square plus y dot square. Here this matrix I call as mass matrix. Now I am going to construct the Hamiltonian. How to construct Hamiltonian? In the earlier case I told you, in Hamiltonian this term will be same. So I am writing this 1 by 2 term here. And I told you, in writing Hamiltonian you have to replace the coordinate by conjugate momentum. So I am replacing this matrix by its momentum, that is px py. Then I am leaving this matrix right now as it is. I tell you, okay, don't worry. And I am replacing this coordinates as px py. In the earlier trick, what we done? We replaced m by 1 by m. Similarly, here I am going to find out the inverse of mass matrix. So I am inverting this mass matrix. So what I get? I will get 1 by m 0 0 1 by m. Now I am going to multiply these matrices, that is h equal to 1 by 2 px py. First I am multiplying these two. So what I get? I get 1 by m into px, 1 by m px plus 0 into py. So it is 0. Then I am taking second row, that is 0 into px, that is 0, plus 1 by m into py, that is py by m. Now I got a column matrix, right? Now again I am multiplying this px py with this matrix. So what I get? I will get h equal to 1 by 2 into px square by m plus py square by m. That is h equal to 1 by 2 into 1 by m p x square plus p y square. See, the same thing we already got by using our earlier trick, that is L is equal to half m x dot square plus y dot square. So what we done? To construct Hamiltonian, we write this 1 by 2 term as it is, and we inverted this matrix. Then we replaced by its conjugate momentum px square plus py square. The same thing we got here also. Okay, so this matrix method is also working, right? Now I am going to use this trick or this matrix method to solve the problem having, or the Lagrangian having, cross terms in the kinetic energy. If kinetic energy contains cross terms, then we can use the earlier trick. So now I am going to try with this matrix method. See, this one is a previous net question, and I am going to solve this problem by two methods. First one is our proper method. Then I solve the same problem by using matrix method. Okay, so in proper method, the Lagrangian is equal to 1 by 2 m x dot square plus m x dot y dot. So what is the first step? We have to identify the generalized coordinates. Right. So what are the generalized coordinates? X is there and the y is there. Next step is find the generalized momenta. That is Px and the Py. And you know what is Px? Px is equal to dou L by dou x dot. And that is equal to, here you see, here there is x dot and here also x dot. So we get mx dot plus m y dot. That is, we get Px equal to mx dot plus my dot. And here, what is Py? Py is equal to dou L by dou y dot. And that is equal to mx dot. So we can find out x dot equal to Py by m. Now I am going to substitute this value here for this x dot. So I get Px equal to m. X dot is Py by m plus my dot. So this will cancels and what I get? I will get y dot equal to Px minus Py by m. Right. So I got y dot value and I got x dot value. Now what is the third step? We know the Hamiltonian H is equal to summation q dot p minus l. So that is equal to, here there are two coordinates x and y. So we get x dot px plus y dot py minus l. And the given Lagrangian is L equal to 1 by 2 m x dot square plus m x dot y dot. So I will substitute this value. So minus 1 by 2 m x dot square minus m x dot y dot. Now what we have to do? We have to replace all the dotted terms because Hamiltonian is a function of q, p and t. There is no velocity terms. Okay. Therefore Hamiltonian will be equal to x dot. X dot is Py by m into Px plus y dot is Px minus Py by m into Py minus 1 by 2 m. X dot square is Py by m all square minus m. X dot is Py by m and y dot is Px minus Py by m. Here you can see these two terms are same. Okay, so it will cancels. So the Hamiltonian will be equal to Px Py by m minus this m and one of the m will cancels. So the remaining is Py square by 2m. So this will be the Hamiltonian. Now I am going to solve the same problem by matrix method. And if you are very much familiar with matrix manipulation, this method is very easy. So the question is, a Lagrangian is given and that is equal to 1 by m x dot square plus m x dot y dot. So here this contains velocity and this also contains velocity. Total kinetic energy is given. There is no potential energy type. So I am rewriting this Lagrangian as 1 by 2 m x dot square plus 2x dot y dot. And once again I am rewriting this equation as 1 by 2 m x dot square plus x dot y dot plus y dot x dot. Now I am going to construct the corresponding matrix for this Lagrangian. So L is equal to, I am taking this 1 by 2 as constant time, and x dot, y dot, and here it is mass matrix. I will fill it later, and this is x dot, y dot. And what will be the mass matrix in order to get this Lagrangian? See, this is the position of x dot square. So in the x dot square there is a mass, that is m, and this is the position of x dot, y dot. So there is a mass m, and this is the position of y dot, x dot, and there is a mass m, and this is the position of y dot square, and there is no y dot square. So the mass is 0 here. So this is the mass matrix. Now what do you have to do next? It is similar to what we done in our first trick. That is 1 by 2 will be 1 by 2 itself. It will be same. See, this x dot and y dot are the generalized velocity. So we have to replace those by generalized momentum. That is px and py. Then we have to invert this mass matrix. And here also we have to replace this coordinates by px and py. So here, what is the inverse of this mass matrix? We know if A is a matrix, and if we want to find out A inverse, then it will be 1 by determinant A into adjoint of A. So by using this method, we can find out the inverse of mass matrix will be 0, 1 by m, 1 by m, and minus 1 by m. Now you just multiply these matrices. So you get h is equal to 1 by 2 px py into 0 into px plus 1 by m into py, that is py by m, and 1 by m into px, that is px by m minus py by m. Now again you have to multiply these matrices. So what do you get? 1 by 2 px into py by m, that is px py by m plus py into this time, that is px py by m minus py square by m. So you will get h is equal to px py by m minus py square by m. See, we got the same answer. So if you are good in some matrix manipulations, then this method will be very easier. And the advantage of this method is you can use this method for any kind of problem. The first trick has a limitation when there is cross terms in the kinetic energy, but this trick don't have any limitations. So you can apply this trick to any problems. But the difficulty is you have to be familiar with some matrix manipulations. Okay. This one is a previous set question. And you see, here we can use our first trick because it is containing cross terms, velocity terms. And it is similar to the earlier case, earlier problem, but now it is minus. So you please do this problem by both the method. Use the matrix method and also use the proper way of solving. This is a work for you. Okay. Another work for you. Find the Hamiltonian of the Lagrangian. L is equal to q dot square by 4 minus q square by 9. Here you can solve by proper method, or you can solve this by the tricky method. So you please try to solve in both ways. Okay. One example problem. A Lagrangian is given. that is m by 2 q dot square sine square omega t plus q dot omega sine 2 omega t plus q square omega square, and given q is equal to q sine omega t. Question is to identify the system. To identify the system, first of all, we are not familiar with this equation. See, L is equal to m by 2 q dot square sine square omega t plus q dot omega sine 2 omega t plus q square omega square. So we are not familiar with this equation. If we can simplify this equation to some other form, maybe we can identify the system. So what we have to do? We have to simplify this Lagrangian and we have to find out its Lagrange's equation of motion. So we can easily identify the system. So how we can simplify this Lagrangian? That clue is given, that is q is equal to q sine omega t. So by using this equation, we can simplify this Lagrangian. How? See, we now q is equal to q sine omega t, and taking its derivative, that is q dot, that is equal to q dot sine omega t plus q cos omega t into omega. Now I am going to take its square, that is q dot square, that is equal to q dot square sine square omega t plus 2 q dot sine omega t into q cos omega t into omega plus q square omega square cos square omega t. Here you can see 2 into sine omega t cos omega t. We can replace this term by sine 2 omega t, right? And I am taking this term to LHS of this equation. So I get q dot square minus q square omega square cos square omega t equal to q dot square sine square omega t plus q dot omega sine 2 omega t. And one q I missed here, that is q dot omega sine 2 omega t. See, this term is here and this term is also here. So we can replace this entire term by q dot square minus q square omega square cos square omega t. Okay, so I am rewriting this Lagrangian, that is equal to m by 2 into, I am replacing these terms by this one, that is q dot square minus q square omega square cos square omega t plus q square omega square. Now again I can rewrite this as m by 2 into q dot square plus, see, q square omega square is a common term. I am taking this outside, that is q square omega square into 1 minus cos square omega t. And what is this 1 minus cos square omega t? That is equal to sine square omega t. So L will be equal to m by 2 q dot square plus q square omega square sine square omega t. And in the question itself, they given capital Q equal to q sine omega t. So this term is nothing but q square. So I can rewrite this Lagrangian as m by 2 into q dot square plus q square omega square. I am expanding this equation, that is L equal to 1 by 2 m q dot square plus half m omega square q square. I think now you are a little bit familiar with this Lagrangian. Right. Now, to identify the exact system, I am considering its equations of motion. So, here the generalized coordinate is q. So, d by dt dou L by dou q dot minus dou L by dou q equal to 0. So, that is equal to d by dt dou L by dou q dot is m q dot minus dou L by dou q is m omega square q equal to 0. That is m q double dot equal to m omega square q. That is q double dot equal to omega square q. I think you are familiar with the harmonic oscillator. That is theta double dot is equal to minus omega square theta, or x double dot is equal to minus omega square x. So here for harmonic oscillator there is minus sign, but here it is positive sign. Okay, so this system is inverted harmonic oscillator. So to identify system, it is better to take the equations of motion. So from the equations of motion you can easily identify the system. Okay. Next topic is Hamilton's equations of motion. You are familiar with the Lagrange's equation of motion? What is Lagrange's equation of motion? It is d by dt dou L by dou q dot minus dou L by dou q equal to 0. Here I told you this time dou L by dou q dot is nothing but p. That is p equal to dou L by dou q dot. And now I am going to substitute this p value instead of dou L by dou q dot. So d by dt of p, that is p dot, and that will be equal to dou L by dou q. So I got two equations from Lagrange's equation of motion. These are very important. And everyone knows Lagrangian is a function of q, q dot and t. Now I am going to take dl. So what we get? We will get dou L by dou q into dq plus dou L by dou q dot into dq dot plus dou L by dou t. Here this term I can replace this term by, see, dou L by dou q, that is p dot, and I can replace this term by p. Okay, so I am going to rewrite this equation. That is dl equal to p dot dq plus p dq dot plus dou L by dou t. Now let us consider one term. That is d of p q dot. What will be this one? This will be equal to p into dq dot plus q dot into dp. So I can rewrite this equation. That is p dq dot equal to d p q dot minus q dot dp. See, now I am going to substitute for p dq dot, this time for p dq dot. So I get dl equal to p dot dq plus d pq dot minus q dot dp plus dou L by dou t. Here you can see this is a d term and here also d term. So I am taking is two LHS of this equation. So I can rewrite d L minus q dot p equal to P dot dq minus q dot dp plus dou L by dou t. Now I am multiplying both sides of this equation by minus 1. So I can rewrite this equation as d q dot p minus L equal to minus p dot dq plus q dot dp minus dou L by dou t. See, this is nothing but our Hamiltonian. What is Hamiltonian? We know h is a function of q, p, t. Now, I am going to find out this dh value. dh. Then dh will be dou h by dou q dq plus dou h by dou p dp plus dou h by dou t. So this both are same equations, right? Left hand side is dh. So we can compare the coefficient of dq, dp and the dh by dt. So what we get? Compare the coefficient. Coefficient of dq is p dot, that is p dot equal to minus dou h by dou q, and next one coefficient of dp, that is q dot, and q dot equal to dou h by dou p, and dou h by dou t is equal to minus dou L by dou t. These are the Hamilton's equations of motion. These are very important. Here I am going to summarize this idea. First we discussed about Lagrangian. And we know Lagrangian is a function of q, q dot and the t. And we know the Lagrange's equation of motion, that is d by dt dou L by dou q dot minus dou L by dou t equal to 0. And we found p will be equal to dou L by dou q dot. This is the generalized momentum. And p dot will be equal to dou L by dou q. Then we discussed about Hamiltonian. And Hamiltonian is a function of q, p, t. There is no q dot terms. Okay. And if we know a Lagrangian, we can construct Hamiltonian, and the equation is summation I q dot p minus L, qi pi. And just now we found the equations of motion, that is q dot equal to dou h by dou p, and p dot equal to minus dou h by dou q, and dou h by dou t equal to minus dou L by dou t. Please don't forget these formulas. These are very, very important. See, in the case of Lagrangian, the equation of motion are p equal to dou L by dou q dot. See, here p don't have any dot, but q have dot. Okay, and another one is p dot equal to dou L by dou q. See, here p has the dot and there is no dot for over q. Okay, and for Hamiltonian, we take q dot, p dot. See, and there is no dot terms. Q dot is equal to dou h by dou p. There is no dot term. Here p dot equal to minus dou h by dou q. There is no q dot term. Okay. So here in this every equation, if LHS contains a dot, then RHS will not contain dot. Right? See, here dot is there, but here no dot. Here LHS contain dot, RHS does not contain any dot. And here RHS contain dot term, LHS contain not dot term. And here LHS contain dot term, RHS doesn't contain dot term. Okay, and for Lagrangian we have P and P dot, and for Hamiltonian we have Q dot P dot. Okay, now we are going to solve some example problem using Hamilton's equations of motion. Okay, I think you remember the equations. That is, one is Q dot, that is equal to dou H by dou P, and the other is P dot, that is equal to minus dou H by dou P, and dou H by dou T equal to minus dou L by dou T. Okay, first example problem, simple pendulum. This one is our simple pendulum, and it oscillates about this axis. So after some time the pendulum will be here, and this angle is theta and length is L. Then what is the Lagrangian? You know Lagrangian is equal to T minus V. So what is T here? I told you trick to find out the kinetic energy. See, this is our plane polar coordinates, and in plane polar coordinates the velocity elements are, one is r dot and r theta dot. Here this L is equal to r, and L is a constant value, so there is no r dot term. Okay, it will be equal to 0. So there will not be any velocities in this direction, but there is a velocity in this direction, that is r theta dot, that is v equal to L theta dot, and here we are choosing this as origin. Then what will be the kinetic energy? Half mv square, that is 1 by 2 m L square theta dot square. Right, now what is the potential energy? This is the potential energy. Height, this height is minus L cos theta. So v is equal to minus L cos theta. Here it is minus because it is in the negative y axis, right? This is negative y. So we can write the Lagrangian, that is 1 by 2 m L square theta dot square plus mg L cos theta. Here I forgot to write this mg. Okay, so we got the Lagrangian, and here you see there is no cross terms, so we can use the trick to find out Hamiltonian. Then what we get? The first term, you write it as itself, that is 1 by 2, and the coefficient of theta dot is ml square, so you have to invert it, that is 1 by m L square, into replace the generalized coordinate by corresponding momentum, that is p theta square, and sign before potential term should be reversed, that is plus become minus mg L cos theta. So this is our Hamiltonian, that is h is equal to p theta square by 2 ml square minus mg L cos theta. Now I am going to solve for equations of motion. Hamilton's equations of motion. So first one is q dot equal to dou h by dou p. That is, here q dot is theta dot, that is the generalized coordinate, equal to dou h by dou p theta. So what we get? We get p theta by m L square. Now what is the second equation of motion? This is first one, and second one is p dot equal to minus dou h by dou q. That is p theta dot equal to minus dou h by dou theta. So this contains theta term, so that will be equal to minus mg L sin theta. Now I am going to take derivative of theta dot. So what I get? I get theta double dot. That will be equal to p theta dot by m L square. Here I know what is the value of p theta dot. That is equal to minus mgl sin theta by ml square. So L will cancel, will cancel. So remaining I get minus g sin theta by L. That is theta double dot equal to minus g sin theta by L. Here I am going to apply small angle approximation. What is it? We are considering sin theta approximately equal to theta. I told you if theta value is very small, then sin theta will be approximately equal to theta value itself. So I can rewrite this as theta double dot equal to minus g theta by L. That is theta double dot is equal to minus omega square theta. We already know this equation. This is equation for harmonic oscillator, right? And we know this omega square is equal to g by L, and therefore omega is equal to root g by L, and the relation between time period t and omega is 2 pi by omega. So we get this is equal to 2 pi root L by g. We solved the same problem by using Lagrange's equation of motion also, right? Are you remembering? If you forgot, please revise the notebooks, because revision is the key point in qualifying the exam. I tell you an example. I'm considering an example of one of the best coaching center in India. So in every batch they took around 600 students, and the maximum of 100 students will qualify, and the remaining 500 fails. See, all the 600 students have the same notes, same class, right? Everything is same. Then why this 500 fails and why this 100 qualify the exam? The reason is hard work. Hard work means revision. You have to revise the subject, then only you can qualify the exam. It is not about the material, or it is not about the coaching center. In every coaching center, some students will qualify. Reason is they are doing this revision. Okay, so please revise the subject properly, because during the time of examination, that is 3 hours, in that 3 hours, you have to remember or recall all the subject. It is a difficult work. So to recall all the equations, all the concepts within the 3-hour time, you should be very much familiar with all the concepts, all the equations. So what you have to do? You have to do revision. So please revise the notebooks again and again and again. Okay. In the class, in the theory class itself, I told you all the possible questions. All the previous questions I told you how to solve, and what is the possible variations I told you, and all the trick I told you. So please revise. Another example, it is spring pendulum. Now what is a spring pendulum? It is similar to simple pendulum, but there will be a spring. This is bob of mass m, and when it is oscillating, after some time the bob will be here, and the length of this spring pendulum is L plus x, and this angle is theta, and mass is m. Then what is the Lagrangian? That is equal to T minus V. So what is kinetic energy T here? We use the trick. That is, here you can see spring is extending and contracting, so there will be a velocity in this direction, that is v1 will be equal to x dot, and is oscillating in this direction, so there will be a velocity v2 that will be equal to L plus x theta dot. Okay, so the total velocity v will be equal to v1 square plus v2 square plus 2 v1 v2 cos theta. Here this v square, and we know this theta is 90 degree here, therefore this time will be 0. So we get v square equal to v1 square, that is x dot square plus L plus x all square theta dot square. So we get kinetic energy T as 1 by 2 m x dot square plus L plus x theta dot square. And what is the potential energy V? Suppose I am taking this point as 0, 0, that is our reference point, then this will be the corresponding potential energy, and this value is equal to minus L plus x cos theta. That is, we will get potential V is equal to minus mg L plus x cos theta. So our Lagrangian L equal to 1 by 2 m x dot square plus L plus x theta dot square plus mg L plus x cos theta. Now we have to construct our Hamiltonian. We can use the trick because there is no cross velocity terms. So Hamiltonian will be equal to, we can take the 1 by 2 term outside. M will be 1 by m into x dot square become p x square plus L plus x is coefficient of theta dot, so we have to take its inverse, that is L plus x into p theta square minus mg L plus x cos theta. Or we can rewrite this as h is equal to p x square by 2m plus p theta square by 2m L plus x minus mg L plus x cos theta, right? Now we have to find out Hamilton's equations of motion. So what is it? First one is q dot, that is equal to dou h by dou p. Here, which is the generalized coordinate? You see, x is a generalized coordinate and the theta is also a generalized coordinate. So we get two equations of motion. One is for x and one is for theta. So first I am taking x, that is x dot will be equal to dou h by dou px. That will be equal to dou h by dou px. Here we have to take derivative, so we get px by m. That we got x dot equal to px by m. Now another equation of motion is p dot equal to minus dou h by dou q. And here also we have two generalized momenta, one is px and one is p theta. So first I am considering for px, that will be equal to minus dou h by dou x. That will be equal to, are you feeling this differential is little difficult? Yes. Then do one thing, please do it by yourself, because I am also very lazy. Okay, do it by yourself and find it. And then you do one thing, you find out this x double dot value. That means here when we are taking x double dot, this term will be px dot by m, and substitute those values there, and please solve equation of motion for this theta term. Okay. Here we are discussing about Hamilton's equations of motion and some more example problems. First one, find Hamilton's equation of motion of given Lagrangian. The Lagrangian is equal to 1 by 2 e raised to alpha t q dot square minus 1 by 2 e raised to alpha t q square omega square. What is the first step? We have to find out the corresponding Hamiltonian, right? And my question is we can use our trick here to construct Hamiltonian from Lagrangian. See, this is the potential energy term, and this potential energy term is time dependent. And I told you, if potential energy is time dependent, then we can use our trick. Okay, but you see here this e raised to alpha t. See here also e raised to alpha t. This e raised to alpha t is a common term for kinetic energy and potential energy. That is, we can rewrite this Lagrangian as e raised to alpha t into 1 by 2 q dot square minus q square omega square. That is, here e raised to alpha t is a common term, common to both potential energy and the kinetic energy. Then you have to take it outside. Then use the trick. So what will be our Hamiltonian? E raised to alpha t into 1 by 2. So we have to write 1 by 2 as itself. Then q dot square, that is p square, and this minus become plus q square omega square. So we got the Hamiltonian. Now we can find out Hamilton's equations of motion. So here only one generalized coordinate, that is q. So q dot is equal to dou h by dou p, and that we will get as e raised to alpha t into p, and we get p dot as minus dou h by dou q. So again you get e raised to alpha t into q omega square, and here you have to find out q double dot. That will be equal to you have to take the time derivative of d by dt of e raised to alpha t into p. Okay, you get this is equal to time derivative of e raised to alpha t is e raised to alpha t into alpha into p plus e raised to alpha t p dot. Then you have to substitute for this p dot value. So you get q double dot will be equal to alpha p e raised to alpha t plus e raised to alpha t into e raised to alpha t q omega square. So you get the Hamilton's equation of motion. Second example problem, Lagrangian is given, that is equal to half m q dot square minus lambda by 2 q dot square. Find the Hamilton's equations of motion. See here we can rewrite this equation because q dot square is common term. So L is equal to 1 by 2 into m minus lambda q into q dot square. Now we can use our trick. So we get h is equal to 1 by 2 into 1 by m minus lambda q into p square. Here the generalized coordinate is q and the corresponding momentum is p. So find the Hamilton's equations of motion. The first equation is q dot is equal to dou h by dou p, and second one is p dot equal to minus dou h by dou q, and then you find out what is q double dot. Here you get this equation of q dot in terms of p. So you have to take one more derivative with respect to time. then substitute for P dot. Then you get Q double dot. Okay, do it by yourself. Another example problem. Here the Hamiltonian is given and H is equal to P square by 2m plus P sin Q. The question is to find out Lagrange's equations of motion. So to find out the Lagrange's equation of motion, first we have to find out the Lagrangian corresponds to this Hamiltonian, right? You know the relation between Hamiltonian and Lagrangian. That is, Hamiltonian is equal to summation Q dot P minus Lagrangian. Now you have to construct the Lagrangian from Hamiltonian. So to find out the corresponding equation, you just interchange these two terms. That is L equal to summation Q dot P minus Hamiltonian. So if we know the Hamiltonian, we can construct the Lagrangian by using this equation. Therefore, what will be the Lagrangian? It will be equal to Q dot P minus Hamiltonian, that is P square by 2m minus P sin Q. And I told you Lagrangian is a function of Q, Q dot and T. And in the Lagrangian, there will not be any P terms. So what you have to do? We have to replace all these P terms by corresponding Q terms or Q dot terms. Okay, then how we can find out the P term in terms of Q or Q dot? Here we use Hamilton's equation of motion. Because in the problem they given the Hamiltonian. So by using Hamilton's equation of motion, we can find out the relation between P and Q. So what is Hamilton's equation of motion? That is Q dot is equal to dou H by dou P. Here see, what is the dou H by dou P? We get it is equal to P by M plus sin Q. Then we can find out this P value, that is P equal to Q dot minus sin Q into M. Now we can replace all the P terms in the Lagrangian by this P. So I am going to rewrite this Lagrangian, that is L is equal to Q dot P. P is M Q dot minus sin Q minus P square, that is M square Q dot minus sin Q all square by 2m minus P is M into Q dot minus sin Q into sin Q. Here you can see this term and this term are common. So again I am going to rewrite this equation. That is L equal to M into Q dot minus sin Q into Q dot minus sin Q minus M square Q dot minus sin Q all square by 2m. Here I can cancel this M square and M, and finally I will get the Lagrangian L equal to M into Q dot minus sin Q all square by 2. So we got the Lagrangian. Then find out the Lagrange's equation of motion. What is Lagrange's equation of motion? That is d by dt dou L by dou Q dot minus dou L by dou Q equal to 0. So please solve this. This is a work for you. See, this one is a previous CSIR net question. The question is, they are given a Hamiltonian, that is h equal to alpha x square p plus p square by 2 into 1 plus 2 beta x plus 1 by 2 omega square x square. And the question is to find out the corresponding Lagrangian. What is the equation to find out Lagrangian? That is L is equal to summation q dot p minus Hamiltonian. Here there is only one coordinate, that is x. So L will be equal to q dot, that is x dot p minus h. Now I am going to substitute for h, that is L equal to x dot p minus h, that is alpha x square p minus p square by 2 into 1 plus 2 beta x minus 1 by 2 omega square x square. Here you can see there is a p time, here also one p time is there. So I am simplifying this Lagrange's equation, that is L equal to p into x dot minus alpha x square minus p square by 2 into 1 plus 2 beta x minus 1 by 2 omega square x square. And I told you Lagrangian is a function of q dot and t. That is, in Lagrange's equation of motion there will not be any p terms. So we have to replace this p terms. So how we can replace? We know Hamiltonian and we know Hamilton's equations of motion. So by Hamilton's equation of motion, we can find out the relation between p and q dot. Then substitute for the p value, then we get the Lagrangian in terms of q dot and t. Okay. So what is the Hamilton's equation of motion? That is q dot equal to dou h by dou p. That is equal to alpha x square plus p by 1 plus 2 beta x. Okay, therefore I can rearrange this equation and I will get p equal to 1 plus 2 beta x into x dot minus alpha x square. Now I am going to substitute this p value in our Lagrangian, that is L equal to p, that is 1 plus 2 beta x into x dot minus alpha x square into this type, that is x dot minus alpha x square minus p square, that is 1 plus 2 beta x all square into x dot minus alpha x square all square divided by 2 into 1 plus 2 beta x minus 1 by 2 omega square x square. See, you can cancel these two terms and what you get? You get L equal to 1 plus 2 beta x into x dot minus alpha x square all square minus 1 by 2 into 1 plus 2 beta x into x dot minus alpha x square all square minus 1 by 2 omega square x square. Here you can see these two terms are same and this differed by this 1 by 2 term. Okay, so this is an important point. When you are converting a Lagrangian to Hamiltonian or when you are converting a Hamiltonian to Lagrangian, the equation just before the final equation will be look like this one. So there you can see two common terms and these two are differed by 1 by 4 or 1 by 2 etc. So even if you made some mistakes in solving this problem and you get one equation for this term and a similar but slightly different equation for this term, then don't worry, yeah, you can easily subtract one from another. So what we get, the final Lagrangian will be equal to 1 by 2 1 plus 2 beta x into x dot minus alpha x square all square minus 1 by 2 omega square x square. So which one is the correct answer? Option A. This one is another net problem. Here one Hamiltonian is given, that is equal to x p square by 2m plus half kx. And the question is to find out Lagrange's equation of motion. So first you have to find out Lagrangian. Then you have to find out the Lagrange's equation of motion. Then what is the equation to find out the Lagrangian? Lagrangian L is equal to summation q dot p minus h. Here which is the generalized coordinate? X. Therefore L equal to x dot p minus h. H is x p square by 2m minus 1 by 2 kx. Now I told you Lagrangian is function of only q dot t. So we have to replace all the p terms, right? So we now Hamiltonian. So we have to find out Hamilton's equation of motion. So we get q dot equal to dou h by dou p. Here q dot is x dot. X dot is equal to dou h by dou p. That is equal to xp by m. So we get p is equal to m x dot by x. Now we can substitute this value here. So I can rewrite this Lagrangian as x dot p, that is m x dot by x minus x p square or x by 2m into p square, that is m square x dot square by x square minus 1 by 2 kx. So here x is there and x square is there, m and m square is there. So we can rewrite this Lagrangian as L equal to m x dot square by x minus this m and m will cancels. Remaining is minus m x dot square by 2x minus half kx. Now we got the Lagrangian. Now we have to find out the equation of motion, Lagrange's equation of motion. That is d by dt dou L by dou q dot. Here q is x dot minus dou L by dou x equal to 0. So first we have to find out dou L by dou x dot. So this dou L by dou x dot will be equal to 2m x dot by x minus m x dot by x, that is equal to m x dot by x. So now we have to find out d by dt of this type, that is d by dt of m x dot by x, that is I am taking this m outside, that is x dot by x. So we can use the u by v formula. So what we get? We get x into d by dt of x dot minus x dot into d by dt of x by x square, that is equal to x into x double dot minus x dot square by x square. Now we can substitute these values here, that is x double dot minus x dot square by x square minus dou L by dou x. Here dou L by dou x is half k, that is plus half k equal to 0. And here I missed this m time, so m into all this time. Okay, now multiply this equation throughout by 2x square. So what we get? We get 2m x double dot minus 2m x dot square plus k x square equal to 0. This one is a gate problem. Here the Hamiltonian is given, that is h is equal to a p square q raised to 4 by 2 plus beta by q square. We have to find out the Lagrangian. So we know Lagrangian is equal to summation q dot p minus h. Here what is the generalized coordinate? Q is the generalized coordinate, that is q dot p minus Hamiltonian, that is a p square q raised to 4 by 2 minus beta by q square. And in Lagrangian there is no p times, so we have to replace this all p times. So what we do? We have to construct Hamilton's equation of motion, that is q dot equal to dou h by dou p, and that will be equal to a p q raised to 4. So we get p equal to q dot by a q raised to 4. Now we have to substitute this value in this Lagrangian, that is L equal to q dot p. P is q dot by a q raised to 4 minus a q raised to 4 by 2 into p square, that is q dot square by a square q raised to 4 whole square minus beta by q square. We can cancel this a square and q raised to 4 and q raised to 4 square. So what we get? We get L equal to q dot square by a q raised to 4 minus 1 by 2 q dot square by a q raised to 4 minus beta by q square. I already told you, see, there are two times. One is 1 by 2 or 1 by 4 of the other type. So what we get? We get Lagrangian L is equal to 1 by 2 q dot square by a q raised to 4 minus beta by q square. So this will be the answer. That is, option A is the answer. Actually, here you don't want to do all those things, because you already know if you are converting Hamiltonian to Lagrangian or Lagrangian to Hamiltonian, the potential energy term will be, the sign of potential energy term will be opposite. So here it is positive. So when we are converting this Hamiltonian to Lagrangian, we get a negative term. So here it is positive. So this is not the answer. Here it is positive, not answer. Here is also positive. Only chance is for option A. This one is a part C net problem, and this one is a little difficult problem, and the question is to find out the trajectory, right? The trajectory of the particle. So a Hamiltonian is given, that is Hamiltonian H is equal to xpx minus ypy minus 1 by 2 x square plus 1 by 2 y square. And the initial values, that is when time t equal to 0, that is the initial values, x0 and y0 will be 1 1, and px0 py0 will be equal to 1 by 2 and minus 1 by 2. So these are the initial condition, that is when time equal to 0, the position of the particle is x equal to 1, y equal to 1, and the momentum is px equal to half and py is equal to minus half. Okay. So here the question is to find out the curves traced out during the motion. Therefore, we have to find out the equation of motion, because these traces will be formed when it is in a motion. So what is the equation of motion? That is Hamilton's equation of motions are q dot is equal to dou h by dou p, and p dot is equal to minus dou h by. So we have to find out q dot. and p dot. Then by integrating q dot, we can find out the q coordinate, right? Similarly, by integrating p dot, we can find out the momentum. So we can find out the relation between x and y and also px and py. Then we can identify what is the trajectory of the particle in xy plane and px py plane. That is what I am going to do. Okay. So we have to find out the generalized coordinates here. So here two coordinates, one is x is there and y is also there. So x dot is equal to dou h by dou px, and that will be equal to x. And what is y dot? Y dot is equal to dou h by dou py, and that will be equal to minus y. And px dot is equal to minus dou h by dou p, that is we get minus px plus x, and py dot is equal to minus py plus y. Now see, what is this x dot? X dot is nothing but dx by dt, that is equal to x, and y dot is nothing but dy by dt, that is equal to minus y. So I am rearranging this equation, that is dx by x equal to dt, and rearranging this equation as dy by y equal to minus dt. Now I can integrate on the both sides. So I get integral dx by x integral dt. So what I get? I will get log x equal to t plus constant, and here what I get? Log y equal to minus t plus constant c2. Now we have to identify what is the value of c1 and what is the value of c2. So how we can find out the value of c1 and c2? By using initial conditions. What is the initial conditions? We know when x equal to 0 and y is equal to y0, the value will be 0, 0. This is at a time t equal to 0, right? So I am taking first equation, that is log x equal to t plus c1. Here I am substituting this condition, initial condition, that is when time t equal to 0, x will be 0, that is log x will be 0 and time is also 0 plus c1. That means c1 equal to 0. So we can rewrite this equation, that is log x equal to t. Now we have to check the other equation, this one, log y equal to minus t plus c2. Again we have to find out what is the c2. So we have to substitute the initial conditions. So we know when t equal to 0, y is equal to 0, equal to minus 0 plus c2. So what we get? c2 is also equal to 0. So the equation will be equal to log y equal to minus t. Equation B. Now I am dividing equation A by equation B. Then what I will get? I will get log x by log y equal to minus 1. That is log x equal to minus log y. And again I can rearrange this equation as log x plus log y equal to 0. That is log of x into y equal to 0. When log of some term is equal to 0, we know log of 1 is equal to 0, right? Therefore, for this equation to be valid, this xy should be equal to 1. Okay, therefore we can say x is equal to 1 by y. This is the relation between x and the y coordinate. See, this is an equation of a rectangular hyperbola. So the relation between x and y, or if you are drawing the trajectory in xy plane, you will get a rectangular hyperbola. Now we have to check for what is the trajectory in px, py coordinates. From the equation of motion, we got px dot equal to minus px plus x and py dot equal to minus py plus y. Here I am rearranging this equation, that is px dot plus px equal to x. And we now log of x equal to t, that we already derived in the earlier case. Therefore, x will be equal to e raised to t. So I can replace this x by e raised to t, that is px dot plus px equal to e raised to t. Now I am going to multiply this whole equation by e raised to t. Then what we will get? We get e raised to t px dot plus e raised to t px equal to e raised to 2t. Here I can rewrite this term as d by dt of px e raised to t. Just check this d by dt of px e raised to t. So we get this equation. So this will be equal to e raised to 2t. Now we can integrate this equation. So by integrating, what we get? We get px e raised to t equal to e raised to 2t by 2 plus c. C is the constant of integration. Now we have to substitute initial conditions. What is the initial condition? One is px0 and py0 will be equal to 1 by 2 and minus 1 by 2 at a time t equal to 0. So we have to substitute these values here. So we get px e raised to t, that is time is 0, equal to e raised to 2t, that is time is 0 by 2 plus c3. So we can find out c3 is equal to 0. That is, the equation is px e raised to t equal to e raised to 2t by 2. Here there is one e raised to t and here also one e raised to t. So we can cancel those values. So we get px equal to e raised to t by 2. Similarly, you can solve for py dot. So you get py will be equal to minus e raised to minus t by 2. Now what will be the px py? Px py will be equal to e raised to t by 2 into e raised to minus t, that is minus e raised to minus t by 2. So what you will get? You will get this is equal to minus 1 by 4. That is, we got px py equal to minus 1 by 4. Again, this is a equation of rectangular hyperbola. Now we can again check the options. So which one is the correct answer? Both are hyperbolas. Okay. This one is another CSIR problem, and this one is a part C problem, and this one is little tricky problem also. Okay. Here one Hamiltonian is given, that is h is equal to p square q square, and the solution of the Hamiltonian equation of motion is given. So what we have to do? First step is we have to find Hamilton's equations of motion. So you get q dot and p dot. Then to find out the coordinate p and q, what you have to do? You have to integrate. Then you get the equations. So the method is very simple, but the problem is you have to do some mathematical manipulations to find out the solution. Okay, if you are very good in mathematics, then it is simple. Nothing is there. The physics is this much only. You have to find the Hamilton's equation of motion. And you know what is the Hamilton's equation of motion. Q dot and P dot. You already know. Then you just find out the Q dot and P dot. Then just integrate. You get the answer. Okay. So first we have to find out Q dot and P dot times. So what is Q dot? Q dot is equal to dou H by dou P. That will be equal to here. What is it? It is equal to 2p q square. And what is p dot? P dot is equal to minus dou H by dou Q. That is equal to minus 2p square q. Here I am rewriting this equation, that is q dot is nothing but dq by dt. That is equal to 2p q square, and p dot is nothing but dp by dt, and that is equal to minus 2p square q. Now I am going to rearrange this equation, that is dq by q. Here one q is there. I am taking this q to left hand side of this equation. That is equal to 2p q into dt. And here also I am rearranging, that is dp by p equal to minus 2p q dt. Now you see, here it is 2p q dt and here it is minus 2p q dt. So I can connect dq by q and dp by p by dq by q equal to minus dp by p. Now I am integrating this function on both sides. That is integral dq by q equal to minus integral dp by p. Then what we will get? We get log q equal to minus log p plus constant of integration, that is log a, because in the question itself they are specified the constants are a and b. So here I am taking this constant as a. Now I can rearrange this equation. I am taking this term to LHS. So log q plus log p equal to log a. That is equal to log of qp equal to log a. Therefore I can say qp equal to a. I got one relation between q and p, right? That is qp equal to a. Now I am going to substitute this value in equation of motion. That is, we got q dot equal to 2p q square and we got p dot equal to minus 2p square q. You can substitute this value in any of this equation. I am taking this one. That is, p dot is nothing but dp by dt equal to minus 2p square q. This is equal to minus 2 qp into p, where this qp is a. So I can rewrite this equation as dp by dt is equal to minus 2ap. Now I am rearranging this equation, that is collecting the p term to the left hand side, that is dp by p equal to minus 2a into dt. Now I am going to integrate. Then what we get? Log p equal to minus 2at plus log b. I am taking this constant as b because in the question they are specified the constants are a and b. So I can collect the log terms, that is log P minus log B equal to minus 280. That is log P by B equal to minus 280. So I'm taking the exponential function on both sides. So I get P by B equal to e raised to minus 280. So what we get? We get P equal to B e raised to minus 280. Now we have two relations. One is P is equal to B e raised to minus 80 and QP equal to A. Then substitute this P value here. Then what we get? We get P is B into e raised to minus 80 equal to A. So we can find out the Q, that is Q will be equal to A by B into e raised to 280. Right, here I made a mistake. I forgot to put this 2. Okay. So we got the relation for Q coordinate and for P coordinate. So what is the answer? Option A. Now we are going to discuss another concept, the Hamiltonian of a charged particle in electric and magnetic field. Suppose this is my charged particle. It is in a 3D space. These are x, y, z coordinate. And this is my charged particle and its charge is plus q. And its position vector is r. And this charged particle is in electric field and in a magnetic field. So if it is in a motion, what will be the kinetic energy of my particle? It will be equal to T equal to half m r dot square, if the mass of the particle is m. And what will be its potential energy? Here you see there is two fields. One is electric field and one is magnetic field. Electric and magnetic field. Therefore, there will be two potential. One is electric potential, that is V equal to Q phi, and magnetic potential is V is equal to minus Q V dot A, where I told you phi is scalar potential and the A is vector potential. We will discuss more about these things in electromagnetic theory. Okay. So what is the total Lagrangian? Lagrangian will be equal to 1 by 2 m r dot square minus q phi plus q into v dot a. Here this v is its velocity r dot. And what is the generalized coordinate in this Lagrangian? It is r. And what will be the generalized momenta? It will be PR. And what is PR? PR is equal to dou L by dou R dot. So what we will get? We get PR equal to MR dot plus QA. So I can find out what is the R dot value. That is R dot equal to V equal to P minus QA vector by M. Just remember this term. I tell you another case. Let us consider a particle is there with the mass m and charge q and is moving in a 3D space, but it is not in a electric or magnetic field. So there is no electric field E equal to 0 and B equal to 0. But it is moving with the certain velocity r dot. Then what will be the momentum? P will be equal to mv. And what will be the v? V will be equal to p by m. And if the same charge is moving in a electric and magnetic field, what we will get? We will get v equal to p minus q a vector by m. That is in E and the B field. Now you can see what is the difference between these two velocities. Here it is P, but here it is replaced by P minus QA. So P become P minus QA in electric and the magnetic field. That is when E is not equal to 0 and B is not equal to 0, and will be P when equal to 0 and B equal to 0. So if the charged particle is moving in an electromagnetic field, then its momentum is replaced by P minus QA. Okay, if you know this concept, you can easily solve one gate problem. See, this one is a previous gate problem and we already solved this problem. Now I told you in magnetic field, when B is not equal to 0 and a charged particle is moving in a magnetic field, then the momentum will be replaced by P minus QA. Now I am going to solve this problem by using this idea. Here the given Lagrangian L equal to m by 2 v square plus CR v vector minus v of r. And in the question it is specified Vr is potential. Here this equation is nothing but the equation of a charged particle in electric and magnetic field. That is L equal to m by 2 v square plus q v dot a minus q phi. So we can use our trick here, that is Hamiltonian equal to. Now when using this trick, we don't want to consider this term. First we have to consider this term, that is we get p square by 2m minus into minus, that is plus q phi. That is P will be P minus QA when the particle is moving in magnetic field. So here this particle is moving in magnetic field, so we have to replace this P by P minus QA. And what is the corresponding QA term here? It is CR. So what will be the Hamiltonian? It will be equal to P is replaced by P minus CR all square by 2m plus q phi. So simple. So if you know this idea, then you can easily solve this problem. In the given problem, this q phi is that is equal to v of r, right? So the final answer is h is equal to p minus cr all square by 2m plus v of r. So I told you the Lagrangian of a charged particle in electromagnetic field is 1 by 2 m r dot square minus q phi plus q into p dot a. Then what is the Hamiltonian? You know the relation between Hamiltonian and Lagrangian, that is h is equal to summation q dot p minus Lagrangian. Here I am not going to solve this problem by this method. Here I told you in magnetic field, if the charged particle is in a magnetic field, the P is replaced by P minus QA. So I am going to write the Hamiltonian directly by using our first trick. That is, This 1 by 2 time will be same, that is 1 by 2, and the m time will be 1 by m, and this r time, that is generalized coordinate, become generalized momentum, that is pr all square. And this is potential, and this will become plus q phi. Here we didn't consider this term, and we know if we consider this term, what is the change in the p? That is p will change to p minus qa. So I am going to rewrite this Hamiltonian, that is h is equal to p become p minus qa all square by 2m plus q phi. So this will be the Hamiltonian of a charged particle in electric and magnetic field. I recommend you to solve and reach to this answer by using our conventional method, that is h is equal to summation q dot p minus L. Okay, you please do this. This is a work for you. So what you have to do? You have to substitute this Lagrangian, then find out the q dot and p dot times, then find out the p value from Lagrangian and substitute here and find out the Hamiltonian. I tell you, you get the same Hamiltonian as this one. You please do it by yourself. Okay. See, this one is the Hamiltonian of a charged particle moving in electric and magnetic field. And this one is corresponds to, first term is corresponds to kinetic energy, and the second term is corresponds to potential energy, and this corresponds to potential energy of electric field. Right. Then there is a question. Where is the potential energy due to magnetic field? I told you electric potential is there and also magnetic potential is there. But in the Hamiltonian, that is the total energy of the system, where is the potential energy due to magnetic field? Where is it? The reason is magnetic forces do not do any work. Suppose there is a spring and you stretching this spring, that is you are doing some work over the spring, then what will happen? It will elongate, and that energy, the work done by you, will be stored as potential energy of the spring, that is half k x square. So potential energy corresponds to the work done. So here the magnetic forces do not do any work, therefore there will not be any potential energy due to magnetic forces. I give you a little more explanation. See, the magnetic force F is equal to Q into V cross B. That is, if this is the magnetic field is pointing into the plane. That is, if this is the arrow, then this is pointing into the plane. That is, what you are seeing is the back side of this arrow. Okay, so it is pointing into the plane. And if there is a charged particle in this field, this is the particle and is moving in this direction, then this is the velocity vector, and V cross B will be point in this direction. That is the direction of force. See, here this is the length element dl and this is the force. So what will be the work done? Work is equal to F dot dl, that is F dl cos theta. What is the theta here? The angle between force and dl is 90 degree. So we get W equal to 0. That is, work by magnetic force is equal to 0. That is why in this equation there is no potential energy term corresponds to magnetic force. Okay. Now we are going to discuss two very important theorems. Theorem 1. If potential energy doesn't depends on time explicitly, that is, potential energy V is not a function of time, then H will be constant of motion. I will give you a simple explanation. We know the relation between dH by dt and dou L by dou t. That is, dH by dt is equal to minus dou L by dou t. This is one of the Hamilton's equation of motion, right? And here we know this Lagrangian is t minus v. That is minus dou by dou t of t minus v. That is equal to minus dou t by dou t plus dou v by dou t. Usually the kinetic energy doesn't contain time explicitly, so this term definitely will be equal to 0. And if the second term dou v by dou t, that is, now we got dH by dt equal to dou v by dou t, and if v is also independent of time, then what we get? This term will be equal to 0. That is, dH by dt equal to 0. When this will be equal to 0? Only when H is equal to a constant. So, if dou v by dou t equal to 0, then dou H by dou t will be equal to 0. That is, H equal to constant of motion. So very important. Okay, this is the first theorem. Theorem 2. If potential energy doesn't depends on velocity explicitly, that is, v is not a function of velocity, then H will be equal to total energy. I tell you the explanation. We know the Hamiltonian H is equal to summation q dot p minus L, and we know this p is equal to dou L by dou q dot, and we know Lagrangian is nothing but t minus v. So I am substituting all these terms here. That is, H equal to summation q dot dou L by dou q dot minus t minus v. That is, H is equal to summation q dot L is t minus v. That is dou t by dou q dot minus q dot dou v by dou q dot minus t plus v. And what is this dou t by dou q dot? We know T equal to 1 by 2 mv square. This is the kinetic energy, and we can rewrite this as 1 by 2 m q dot square. that is dot T by dot Q dot will be equal to M Q dot, and Q dot into dot T by dot Q dot will be equal to M Q dot square. Q dot is V. So this is mv square, that is equal to 2T. So I can rewrite this equation, that is H equal to Q dot T by dot Q dot is 2T. 2T minus Q dot dot V by dot Q dot minus T plus V. So what we get? We get H is equal to 2T minus T, that is T plus V minus Q dot dot V by dot Q dot. Therefore, if this term, that is, Q dot is nothing but velocity. So, if the potential energy V is not a function of velocity, then this term will be equal to 0. So what we get? We get H equal to T plus V. That is, T plus V is kinetic energy plus potential energy, that is equal to total energy. So when potential energy is independent of velocity, then Hamiltonian will be equal to total energy. That is, if V is not a function of velocity, potential is not a function of velocity, then Hamiltonian will be equal to T plus V. That is, H will be equal to total energy, E total. See, this one is a previous net question and this is a part B question. That is, this is a 3-mark question. Now, what is the question? The question is, the Hamiltonian of a system with n degrees of freedom is given by Hq1, Q2, etc., P1, P2, and T with an explicit time dependence on time T. Okay, so this Hamiltonian is dependent on time, that is explicit dependence on time, right? Then the question is, which of the following is correct? Now check. First option. Option A, different phase trajectories cannot intersect each other. When we are discussing about phase space, I told you different phase trajectories cannot intersect each other. But here this is not correct. Why? Here, see, this Hamiltonian has explicit dependence on time. And I told you Hamiltonian is most of the cases is equal to total energy. So we can say total energy is dependent on time. That is, as time increases, maybe the total energy of system increases, or as time increases, the total energy of system maybe decreases. So the total energy of the system is not constant. If it is not constant, we cannot say this thing, different phase space trajectories cannot intersect each other. When we are solving the phase space problems in the earlier lecture, we took one condition. What is it? We took kinetic energy plus potential energy is equal to total energy and is equal to constant. Okay, we took this condition, then only we drawn all the trajectories. So for this condition only, these different phase space trajectories cannot intersect each other. But here energy is not constant, energy is dependent on time. Second one, H always represents the total energy of the system and is a constant of motion. Nope, we can say, what is constant of motion? Dou H by dou T should be equal to 0. Then only we can say H is a constant of motion. But here H has explicit time dependence. So this will not be equal to 0. So option B is also not correct. Option C, the equations. These are the Hamilton's equation of motion are not valid since H has explicit time dependence. And see, it is not valid. When we derived this equation, that is Hamilton's equation of motion, we started from a Hamiltonian similar to this one. So, a Hamiltonian which contained time. So, from that one only we derived this equation. So, we cannot say it is not valid because it is valid. Okay, and then then definitely the option D will be the correct answer, right? Maybe you have the doubt why it is correct. What is option D? Any initial volume element in phase space remain unchanged in magnitude under time evolution. Are you remembering our Liouville's theorem? We discussed this theorem in phase space. What is it? The theorem tells d rho by dt equal to 0. That is rho equal to constant. What is this rho? Rho is the density. So density is not changing. That means volume element will not change. Okay. So option D is the correct answer.